Yes.
Okay, so I'm gonna, I guess, go back to talking about high throughput experimentation and my views on where the field has been and where we may be headed in the future. So I do thin film work, and we look for try to discover new functional materials such as permanent magnets, piezoelectric materials, and sometimes superconductors. And today's story, a little bit of story that I'm going to tell you about, is done in collaboration with Gilad Kuzny at NIST, Valentin Stanev at Maryland, and Apurva Mehta at SLAC, and you heard from Stefano. Okay, so we've been hearing all day. The good news is, well, we've been at this for some time now, something like 20 years. And of course, we heard about great new techniques being developed, but it turns out, if you look around, you take any materials topic and it's probably been explored, maybe not necessarily successfully by somebody. And the community is always getting bigger, this high throughput material science community. But we kind of know each other. So if you're interested in jumping in, you can just ask one of us and we can tell you who may have tried successfully or unsuccessfully. Just some materials are really difficult to study in a high throughput manner, but we always try to do it. And of course, there are many, meetings where we get together and talk about the greatest hits. And this is just one example, but what I can say is this meeting and the atmosphere has transformed quite a bit in the last 5 to 6 years, I would say. And it's largely due to the advent of MGI. And so whereas it used to be, we would all get together, experimentalists mostly, and talk about, how to make materials really fast, and measure them fast. But now it's equally divided, not divided, we all together, but in terms of participants, it's experiments, theories, and AI methods, of course, dominate the topics, of course. And really important background story is that China is pumping in billions of dollars. They call it material genome engineering. And at least the experimental high throughput part, I know it's a couple $100 million distributed over tens of universities. And I know it started back in 2018 and it's beginning to take shape. And Chinese science is high level science now these days. And of course, in the backdrop, the interesting news is that what we consider to be a premier journal in the field, ACS COMBI, decided to close in 2020. And of course, the argument is that COMBI has become an integral part of every field. So it's no longer needed to, such specialized journal. I kind of disagree. I think material science has moved to a point where materials method is a genuine subfield of material science. So I think that's what combinatorial science this journal was serving. So perhaps it'll be reborn into some other journal like materials methods or something. Of course, so the interesting thing that I talked to Stefano about is how to integrate theory and experiments. Now that computational work is also done in a high throughput way, why not set up this dual track parallel attack kind of approach to materials, rapid exploration and discovery? And of course, you want to have as many of these nexus points as possible. And so the idea is if you want to do validation work, why not use a combinatorial library so that you're measuring a larger potential sweet spot? And if you want to give data to the computational colleagues so that they can build models, why not give them homogeneous data taken out of combinatorial libraries, right? So we want to be able to do experiments. We're guided by something, and we heard a lot about theoretical guidance, but in some material system, such as superconductors, there just aren't that many good theoretical predictions. And when that's the situation, you need to turn to experimental databases and so that you can look for trends and hopefully start to build predictions. The problem is, in terms of functional materials, there are very few well-curated experimental databases. And so you need to think about even like building your own materials databases. And here are a couple of exceptions. Starry Data is a thermoelectric materials database. And Matt Navi out of NIMS in Japan has a large compendium of a variety of functional materials databases. And so we've been able to use one of these, in particular, the superconductor ones, and we were able to download 29,000 entries of experimental data points. And so with that, you can begin to build, reasonably reliable, hopefully, predictions. And with that, we can go about charting the course for experimental search using the high throughput technique. And but because we, like I said, there are very few well-curated databases in the community. We started talking about using natural language processing. So feed computer, hundreds to thousands of PDFs of papers, right? And let the machine build a database. And so we actually looked into doing something like this also a while ago with respect to permanent magnets. But what we found is that while this software works really well, what you really need, the really critical information are in graphs and tables. So that's different from just, computer reading the text. And so this is the realm of machine vision, where I hear that there's been great strides made, but I think there's still a lot more to be done, where you can reliably feed a PDF of a paper to a computer and it spits out tabulated, downloadable database from, complicated, multicolored, three-dimensional plots of data, right? Okay, so let me go back to talking about experiment. So we've been applying unsupervised machine learning to diffraction data, in particular synchrotron diffraction data, because the beam time is kind of limited and we like to be able to do rapid analysis. And so a few years ago, led by Gilad Kuzni, we demonstrated this dynamic analysis of a diffraction. That is, so we start analyzing the data as we are doing the sequence of measurement. And so after all the measurements are done, say we can measure 200 compositions, mapping a compositional phase diagram in 2 hours, right there and then, we already have sort of an initial cut of what structural phase distribution, that's sort of the ultimate goal. One ultimate goal of material science is to rapidly map structural phase diagram. And we have an initial cut of something right after the measurement. Now we no longer have to wait to go home and do post-mortem, so to speak, analysis of the data. We can analyze the data right there and then. And this has changed the way we're able to design and schedule our experiments at the synchrotron. And actually, this is the kind of material system we're interested in. So we're interested in functional smart materials that derive their functionalities from being at the phase boundary. So this is the fictitious phase diagram, but wouldn't it be interesting if you can find the material that sits over here? And so what happens is, because it's right at the boundary, material is sort of suffering from identity crisis. And because of that, just with a small nudge of field or temperature or composition, you get huge susceptibility. And that's how you derive the functionality in shape memory alloys and morphotropic phase boundary piezoelectric materials, et cetera. So that's the kind of materials we're interested in. And so all the more reason we want to spend a lot of time doing synchrotron measurements. So Benji talked about his pioneering autonomous materials exploration. So we've been applying this to our combinatorial libraries. So it turns out, because on our libraries, because samples are laid out in neatly arrayed manner, it's particularly amenable to applying active learning. And so the idea here is that we want to reduce the amount of time that it takes to do the measurements. So instead of setting out to measure every single point, so now diffraction is not too bad, it's streamlined, we could do it quickly. But many other characterization techniques, it takes a long time actually. It's, full disclosure, it's mid-throughput at best, right? So if you measure and characterize every single point of a material's energy band gap, let's say, it could take up to days to a week. And so it would be nice if you can reduce the number of experiments. So here what we do is we make the library, we do initial sprinkling of measurements, and at this point we already start applying unsupervised machine learning, start building the phase diagram. And then we let the algorithm dictate what experiment we should do next, so that we can maximize the information with respect to the goal of the experiment. And in this case, the idea is to rapidly map the phase diagram. Okay, so this is actually an example. So this was simulation, but using real data, right? Because you can set up the arrays of diffraction data, and then you can key them in whatever way you want. And so on the left, what's shown is the measurement points that are being filled up. So the sequence with which the points are being filled is determined by this active learning algorithm. And on the right is after each measurement, it gives us what he thinks is the distribution of structural phases. So what's interesting here is that, well, first of all, they're only about 200 points. So by the time you measure 100 points, this classification error should be reasonably low. But what's interesting here is that if you stop here right at the beginning, so let's say that's 1/10 of all the measurements, right? Maybe between 1/5 and 1/10. So if you look at this answer, or what he thinks is the answer, it's actually not too far off from the correct answer. So what this says is that you don't actually have to measure every single point. 1/10 of the way, if we're lucky, usually it's about 1/5 of the way into the measurement, you get the answer more or less to what you're looking for. And then if you look at what's happening on the right here, you see these big bright squares showing up, right? So these are the points where the algorithm told us to go measure. And what you notice here is that they always land on the phase boundaries, which makes sense, right? Because we're telling the algorithm to figure out the phase distribution. So naturally, you would gain maximum knowledge by going to the phase boundary where you're uncertain about which particular phase a particular composition belongs to. So at this juncture, we have an algorithm that gives us the answer as to where martensites are, where morphotropic phase boundary piezoelectric materials are, where magnetostrictive materials are. Okay, so this is what we use to let the algorithm navigate how we would look for new functional materials. So most recently, we were able to demonstrate this live, measuring the diffraction to do phase mapping at SLAC, while at the same time within the same loop, we're characterizing a particular physical property, in this case, the energy gap difference between crystalline and amorphous phase. So the particular topic here that we tackled was a phase change memory material. So you want to maximize the band gap difference between the crystalline and amorphous phase. And then what we were able to show here is that we were able to apply this, the basic tenet that maximum or optimum property resides either at the phase boundary, like in many smart materials, or right smack in the middle of a particular phase. And so with this experiment, again, we were able to show that just with a fraction of the points, we didn't have to map all the points. We got to the answer, and we actually found a new material, this GST 467, which you can see sits right at the boundary. And it looks like it's just maybe a measurement artifact, but we reproduced this many times in multiple spreads done over 6 months. And we've also reproduced it. We made actual photonic devices out of it, and we show that it's actually better than industry's benchmarked GST 225. So of course, autonomous experimentation could be used to optimize the materials processing, but it could actually be used to discover a completely new solid state compound. And sometimes when we are lucky, you can actually discover something that's better than the existing materials. Okay, so I'm almost finished here. So again, we heard a lot about great advances in additive manufacturing and its application to high throughput. But in terms of more standard synthesis and characterization, if I look back at the history of this field, back 20 years ago, we were dealing with this. Well, it was always about the number game. How can we make large number of samples? And are we sure that when we make 1,000 samples, half of them are not garbage material? These were the questions we were grappling with. And then, of course, for the longest time, we had to, challenge us to do the rapid measurement, and can we do quantitative measurements? And then by 10 years ago, though, we were squarely dealing with this situation of what do we do with all this data now that we got it, okay? And then so a few years ago, again, with Benji's pioneering experiment, we learned that autonomous is the way to go. And so now we are finally able to reduce the number of experiments. We're besting the number game now. So I think it's still good to try to make large number of samples, but at least in terms of measurements, we don't need to measure every single point anymore. We're going back the other direction. We're able to reduce the number of experimental data points. And and this is, you know, we're never sure about the funding situation. So it's always good to be able to reduce the amount of resources, amount of time, amount of labor to do experiments. So we think we will always be, deploying this kind of experimental approach. And we're trying to move into the area where we're actually doing a synthesis of the library and characterization at the same time. That would be really the goal. Okay, finally, I just wanted to find out that we talked about educating the workforce, next generation workforce. So we've been running this machine learning summer camp with a focus on experimental data, actually, for 5 years now, funded by Jim Warren. And so we've had actually over 400 participants to date. And this year, of course, it was on Zoom, but what that meant was we had the largest class so far. We had 180 people from around the world. And so if you're interested, you can write to me or you can go to the Nano Center website. And that's it, I'll stop there. Thank you.
Okay, thank you. Benji, we are really pushing up against our time limit.
Okay.
So if you can